Next, we discuss about the varistor resistors. A varistor, also known as a voltage-dependent resistor (VDR), is a special type of resistor whose resistance varies with the applied voltage. Unlike regular resistors that follow Ohm's law, varistors have a nonlinear resistance voltage characteristic. They are primarily used for surge protection in electronic circuits, absorbing excess current and limiting voltage spikes. Varistor resistors are non-ohmic behavior. Varistors do not follow Ohm's law, meaning their resistance changes with the applied voltage. As voltage increases, the resistance decreases non-linearly. A varistor is a nonlinear resistor made of semiconductor and current through which depends non-linearly on the applied voltage across it. It means, a varistor is indeed a type of nonlinear resistor, typically made from semiconductor materials like metal oxides, example, zinc oxide, where the current flowing through it is not directly proportional to the applied voltage. This nonlinear behavior is crucial for its use in voltage surge protection and transient suppression. We know the definition of surge protection. It means varistors are commonly used as surge suppressors to protect sensitive electronic components from voltage surges caused by lightning, discharges, or inductive loads. The resistance of a varistor is highly dependent on the applied voltage. At low voltages, the resistance is high, but it drops dramatically as the voltage increases. Metal oxide varistors (MOVs) are indeed the most commonly used form of varistor resistors. They are widely used for transient voltage protection in electronic circuits due to their ability to significantly change resistance with voltage. MOVs are made from ceramic materials containing metal oxides like zinc oxide, and other oxides like bismuth, cobalt, and manganese. They are sandwiched between two metal plates or electrodes. A varistor, also known as a voltage-dependent resistor (VDR), is a type of resistor whose resistance changes with the applied voltage. Specifically, its resistance decreases as the applied voltage increases. This characteristic makes them useful for protecting circuits from voltage surges and transients. These are generally used as safety devices to prevent excess transient voltage in the circuit so that the components of the circuits remain protected. It even controls the operating conditions of the circuit. Varistors, also known as voltage-dependent resistors, are used as safety devices in circuits to protect components from excessive voltage surges and transients. They act as a clamping mechanism, shunting excess current away from sensitive components when the voltage exceeds a certain threshold. This helps maintain stable operating conditions and prevents damage to the circuit. A varistor is a voltage-limiting protection device. By using the nonlinear characteristics of a varistor, when an overvoltage occurs across a nonlinear varistor, the varistor can clamp the voltage to a relatively fixed value, thus protecting the back-end circuit. Varistors are indeed a type of resistor, specifically a two-terminal semiconductor component, and they're used to protect electrical and electronic devices from overvoltage transients. They are also known as voltage-dependent resistors (VDRs) because their resistance changes based on the applied voltage. Varistors are designed to shunt excess current when a surge or spike in voltage occurs, preventing damage to the protected device or circuit. This is called over-voltage protection. A varistor, also known as a voltage-dependent resistor (VDR), is a nonlinear resistor whose resistance changes with the applied voltage. Typically, its resistance decreases as voltage increases, and this reduction becomes drastic when the voltage exceeds a certain threshold. This behavior makes them useful for protecting circuits from voltage surges. Varistors, also known as voltage-dependent resistors (VDRs), are surge suppressors that protect sensitive circuits from voltage surges, including those caused by lightning strikes and electrostatic discharges (ESD). These components have a high resistance at normal operating voltages and a drastically lower resistance when exposed to high voltage surges. This behavior allows them to shunt excess current to ground, preventing damage to the protected equipment. This image shown is varistor resistor. Varistors are used as control or compensation elements in circuits either to provide optimal operating conditions or to protect against excessive transient voltages. When used as protection devices, they shunt the current created by the excessive voltage away from sensitive components when triggered. The varistors are typically constructed using a ceramic material, often zinc oxide (Zn), with the small amounts of other metal oxides. The ceramic material is sintered into a compact structure and which creates a network of grain boundaries. The image shown as the standard symbol for a varistor in a circuit diagram is a zigzag line, similar to a resistor symbol, with two parallel lines extending from either side of the zigzag. This symbol represents the varistor's dual nature as a voltage-dependent resistor. Next, we discuss about the principle of varistor. A varistor is a non-ohmic resistor. A varistor's resistance changes with the applied voltage, unlike a standard resistor where resistance remains constant. This nonlinear relationship means that a varistor does not obey Ohm's law, which states that the current through a conductor is directly proportional to the voltage across it. We know the Ohm's law. Ohm's law V is equals to IR describes the relationship between voltage V, current I, and resistance R in a circuit where resistance is constant. Here varistors are non-ohmic resistors, do not exhibit a constant resistance value. Their resistance changes with changes in the applied voltage. The main difference between a normal resistor and a voltage-dependent resistor varistor lies in how their resistance changes. Normal resistors have a fixed resistance value that is not altered by the applied voltage, while varistors, also called voltage-dependent resistors, have a resistance that changes in response to the applied voltage. The resistance of a normal resistor is primarily determined by its physical properties, material, length, cross-sectional area, and remains relatively constant as long as the temperature and current remain within its rated limits. You can change the resistance of a normal resistor only by physically replacing it with a resistor of a different value. A varistor's resistance changes as the voltage across it changes. Their resistance typically decreases as the applied voltage increases, making them suitable for surge protection and voltage control applications. This resistance change is a nonlinear phenomenon, meaning the resistance doesn't change proportionally with the voltage. The final conclusion is the resistance of a varistor is not a constant property, but rather a dynamic one that responds to the applied voltage, allowing it to change its resistance in real time. Next, we discuss about the advantages of varistor. First one. It can be used to protect the electrical components of an electric circuit, particularly from transient voltage spikes and surges. Varistors, also known as metal oxide varistors (MOVs), are designed to absorb and dissipate energy from these voltage spikes, preventing damage to sensitive components. Varistors are used as control or compensation elements in circuits either to provide optimal operating conditions or to protect against excessive transient voltages. When used as protection devices, they shunt the current created by the excessive away from sensitive components when triggered. Second one, it provides surge protection to the AC and DC motors. Simply, a varistor, also known as a voltage-dependent resistor (VDR), or metal oxide varistor (MOV), provides surge protection to both AC and DC motors. Varistors are designed to limit voltage spikes by absorbing excess energy and reducing their resistance when voltage exceeds a certain threshold, thereby protecting the connected device. Next, we discuss about the disadvantages of the varistor. First one, a varistor primarily provides overvoltage protection and does not offer protection from excessive current during a short circuit. When a short circuit occurs, the current flow is usually very high, and a varistor, while able to clamp over voltages, is not designed to handle the sustained high currents of a short circuit. Second one, while varistors are effective at protecting against voltage surges, they are not typically designed for protecting against current surges specifically during device startup. Varistors primarily act as voltage suppressors, clamping voltage spikes to a safe level, and their current handling capabilities may be insufficient for the high inrush currents that can occur during device startup. Third one, a varistor, while effective at protecting against voltage spikes and surges, is not designed to protect against voltage sags, also known as brownouts. Varistors primarily clamp high voltages, but they don't react to sustained lower voltages that characterize voltage sags. Next, we discuss about the applications of varistor. First one, surge protection. It means varistors are commonly used to protect circuits from voltage spikes transients. When the voltage exceeds a certain threshold, the varistor conducts and diverts excess energy away from sensitive components, preventing damage. Second one, electronic device protection. It means, in devices like TVs, computers, and mobile chargers, varistors shield internal circuits from sudden voltage surges caused by lightning, power grid fluctuations, or switching operations, ensuring device longevity. Third one, inductive load switching. It means, when devices with coils, motors, transformers, relays are turned off, they can generate high voltage back EMF. Varistors absorb this energy, protecting switches and semiconductors from damage. Fourth one, power supply protection. It means, power supplies often face input voltage fluctuations. A varistor at the AC input line suppresses voltage surges, preventing them from reaching the rectifier and voltage regulation stages. Fifth one. Relay and contact protection. It means switching inductive loads with relays can cause arcing and voltage spikes across the contacts. Varistors reduce this arcing by clamping the voltage, thus extending the life of the relay. Sixth one. Lighting systems. In LED and HID lighting systems, varistors prevent damage from power surges or lightning strikes. They are especially important in outdoor lighting where such disturbances are common. Next, we discuss about the photoresistor or LDR. LDR means light-dependent resistors. A photoresistor, also known as a light-dependent resistor (LDR), or photoconductive cell, is a light-controlled variable resistor. Its resistance changes based on the intensity of light it's exposed to. Specifically, the resistance generally decreases as the intensity of incident light increases. A photoresistor is a semiconductor device that can change its resistance when exposed to light. Photoresistors, also known as light-dependent resistors, exhibit a characteristic where their resistance decreases as the intensity of incident light increases. This phenomenon is based on the principle of photoconductivity, where light absorption by the semiconductor material increases the number of charge carriers, thus lowering the electrical resistance. Photoconductivity means photoresistors are made from semiconductor materials that can conduct electricity when exposed to light. When light shines on the material, photons are absorbed by electrons, giving them enough energy to break free from their bonds and enter the conduction band. An LDR, light-dependent resistor, is indeed an electronic component that responds to light. It's also known as a photoresistor. The LDR's resistance changes based on the intensity of light falling on it. Specifically, its resistance decreases as the intensity of light increases. LDRs are electronic components whose resistance changes when light shines on them. Specifically, as light intensity increases, the resistance of an LDR decreases. This property is due to the phenomenon of photoconductivity, where the material of the LDR becomes more conductive when exposed to light. As more light strikes the LDR, more electrons are excited, and the material becomes more conductive. Since conductivity is the inverse of resistance, the resistance of the LDR decreases as light intensity increases. The resistance of a light-dependent resistor (LDR) can change significantly over multiple orders of magnitude, with resistance typically dropping as light intensity increases. In darkness, an LDR's resistance can be in the megaohm range, e.g., several million ohms, while in bright light, it can decrease to a few hundred ohms or even less. This wide range of resistance values makes LDRs suitable for various applications that require light level detection or control. The resistance of a light-dependent resistor (LDR) decreases as the light intensity increases. In the dark or at low light levels, an LDR has a high resistance, limiting the flow of current. As the light level increases, the LDR's resistance drops, allowing more current to flow. This behavior is due to the principle of photoconductivity, where light causes electrons in the semiconductor material of the LDR to become free and move, thus increasing conductivity and decreasing resistance. A light-dependent resistor (LDR) exhibits a significant change in resistance when exposed to light. In the dark, its resistance is very high, typically in the megaohm range, while in bright light, it drops dramatically, often to a few hundred ohms. LDRs are designed to change their resistance based on the amount of light they receive. When no light is present, the LDR's resistance is very high, sometimes reaching several megaohms. When exposed to bright light, the LDR's resistance decreases dramatically, often to a few hundred ohms. The ability of certain resistors to change their resistance value, like light-dependent resistors (LDRs) or thermistors, makes them useful in various applications. These resistors can be used to detect light levels, measure temperature, or control current and voltage in circuits. Next, the topic of photoresistor will be continued. The sensitivity of a light-dependent resistor (LDR) changes with the wavelength of the incident light. LDRs are nonlinear devices, meaning their sensitivity varies depending on the wavelength of the light falling on them. Different LDR materials have different spectral response curves, meaning they are more or less sensitive to different wavelengths of light. For example, some LDRs are designed to be particularly sensitive to infrared radiation, while others are more sensitive to visible light. The design of light-dependent resistors (LDRs) utilizes semiconductor materials to achieve their light-sensitive properties. LDRs are essentially resistors whose resistance changes in response to light intensity, and this variation is achieved through the light-induced behavior of semiconductors. LDRs are typically made from semiconductor materials like cadmium sulfide (CdS) or cadmium selenide (CdSe). While cadmium sulfide (CdS), lead sulfide (PbS), and indium antimonide (INSB) are indeed materials used in resistors, particularly light-dependent resistors (LDRs) or photoresistors. Additionally, other semiconductor materials like silicon and germanium can be used in LDRs. Next we discuss about the symbol of LDR. The LDR symbol in electronic circuit diagrams is indeed based on the resistor symbol, but it includes arrows to visually represent the light rays impinging on the device. These arrows, similar to those used in symbols for phototransistors and photodiodes, indicate the light source and its interaction with the LDR. This visual representation helps distinguish the LDR from a regular resistor on a circuit diagram. The image is shown as a light-dependent resistor (LDR), also known as a photoresistor or photocell. It is a type of resistor whose resistance changes depending on the amount of light incident on it. An LDR's resistance decreases as light intensity increases. It works based on photoconductivity, where light absorption excites electrons, increasing conductivity. The circuit symbol for an LDR typically includes a circle with a resistor inside and arrows indicating light. Next, principle of light-dependent resistor. The working principle of an LDR light-dependent resistor is photoconductivity, an optical phenomenon where the conductivity of a material increases when it absorbs light. Specifically, light photons with sufficient energy cause electrons in the material to move from the valence band to the conduction band, increasing the number of charge carriers and thus the conductivity. This, in turn, leads to a decrease in the LDR's resistance. The phenomenon where a material's electrical conductivity increases due to the absorption of light is called photoconductivity. When light is absorbed, particularly by semiconductors, it excites electrons into higher energy states, increasing the number of free charge carriers and thus enhancing the material's ability to conduct electricity. When light shines on a light-dependent resistor (LDR), the light photons excite electrons in the LDR's valence band, allowing them to jump to the conduction band. This increases the number of free charge carriers, leading to a decrease in the LDR's resistance. For an electron to be excited and jump from one energy band to another in a material, the incident light's photons must possess sufficient energy, exceeding the material's band gap. This band gap represents the minimum energy required to move an electron from the valence band to the conduction band. When light with sufficient energy greater than the material's band gap shines on a semiconductor, it can excite electrons from the valence band to the conduction band, creating more charge carriers. This increase in charge carriers leads to a decrease in resistance of the material. This process is the fundamental principle behind devices like light-dependent resistors (LDRs). The resistance of a device decreases when increased current flow causes a process, like heating, to reduce the resistance. For example, in a light-dependent resistor (LDR), increased light intensity excites more electrons, leading to more current flow and lower resistance. In most materials, increased current can also lead to increased temperature, which can initially increase resistance. Next, we discuss about the advantages of LDR. LDR's light-dependent resistors offer several advantages: high sensitivity to light, a simple and compact design, ease of use, and low cost. They are readily available and suitable for a wide range of applications, from basic light sensing to automatic lighting control. First advantage: high sensitivity to light. It means LDRs are highly sensitive to changes in light intensity, making them suitable for applications where precise light detection is needed. Second advantage: simple and compact design. It means LDRs are straightforward in design and are small, making them easy to integrate into circuits. Third advantage: easy to use. It means LDRs can be easily incorporated into electronic circuits. Complex setup or specialized knowledge. Fourth advantage: inexpensive. It means LDRs are relatively inexpensive manufacture and purchase, making them an economical choice. These are the advantages of light-dependent resistor.